So today we're going to be talking about Chapter 11. So Chapter 11 is all about the complex numbers. So remember that the complex numbers are things of the form a plus bi, where a and b are real numbers, and I is the imaginary number that's equal to the square root of -1. Right? That should be a review from your Algebra 2 course. So one of the weird things about the complex numbers is like the ordering principle. So like if I ask you which is bigger, 3 or 4, what would you say? 4, right? Yeah. Because if I draw the number line, like 3 comes before 4, right? But what if we ask which is bigger? Three plus 2i or 2 plus 3i? Why? But 2 smaller than 3.
I is the square root of 1.
Yeah, that's what I is. That is true. Here's the problem, right? Is that we have this real component and we have this imaginary component, right? So if I try to order these things on a one-dimensional system, like a number line, it doesn't work, right? Like you can't order them. This kind of equation doesn't make sense. What you would need in order to place these is, instead of a number line, you need like a plane. So if we do that, and the x-axis here we call the real axis, because we're going to plot the real part of our complex number on that one. And the y is the imaginary axis, because we'll plot the imaginary part of our complex number on that. So 3, 2 would be the complex number 3 plus 2i, and 2, 3 would be the complex number 2 plus 3i. What's this kind of starting to remind us of? The three-dimensional graph? How many? Okay. Well, that's true, yes. Let's think a little bit more broadly, right? So the complex number has 2 components, right? A real component and an imaginary component, right? What other mathematical structure has 2 components like that?
Oh, the one vector.
Vectors, yeah, that have like an x component and a y component, right? So it turns out that very much so, everything that we can do with vectors, we can do with complex numbers kind of in the same fashion, right? So for example, if I wanted to add the numbers 2 minus I with 1 plus 2I. Well, two minus I would be here, right? And if I go from there and I like add them head to tail like I would a vector, so if I imagine like that's a vector, so I'd go 1 over and 2 up. So this guy is my resultant vector, which would be at the point 3, 1, right? But what do you, that seems like a convoluted way of doing that graphically, right? What did we really just do? Added the real parts, and then added the imaginary parts. And that's all there really is to it. Oh! Okay. That's pretty easy. So like the standard form, or this complex, these complex numbers, written in this kind of standard way as a plus bi, is basically the same as like the component form notation for a vector, right? Everybody kind of see the same thing? When we talked about vectors, so we could define a vector with its component form, right? And what was another way we could define a vector? Okay, like a linear combination or like that, yeah, sure. What's another way? The first way we talked about, even before component form. Magnitude and direction, right? So what is magnitude when we talk about when we talk about a vector? Yeah, that distance from the terminal point of our vector to the origin, right? Now remember way back in like our Algebra 1 class, if I wanted like the absolute value of -3, we define that as the distance from the argument to 0 on the number line, right? Everybody's okay with that? So let's take that and translate it to a complex number. So let's say this is the complex number a plus bi. This distance then from the complex number to the origin should be the same as the absolute value of a plus bi, right? And that is really the same as the magnitude of a vector, right? Because we're talking about doing the same thing. So how would we calculate that then? How did we do that for a vector? Well, we just took the square root of the x component squared plus the y component squared. And depending on the textbook, instead of the phrase absolute value, you might see modulus or even maybe the term norm. Those kind of three terms could be used interchangeably, depending on the context anyways. They're not the same thing. The absolute value is like the most specific, and modulus and norm are like a bigger term, but include would it mean the same thing as an absolute value in a one-dimensional sense. You know what I'm saying? Like, that's a golden retriever. Okay, that's a dog. Okay, that's also true, but the dog includes the fact that it could be things other than golden retrievers, right? That's kind of what I'm saying here. So that's really easy, like figuring out the magnitude of one of these complex numbers. The other thing that we wanted to talk about was the direction. Theta was that value, right? If we're thinking about a complex number as a vector, if I'm talking about magnitude, I'm also interested in a direction. So if that's true, then tan theta should just be the y component over the x component. Everybody's okay with that idea? So if I take those two, the absolute value of a vector and the direction of a vector, we can create a new way to describe our complex number. So for some complex number, and kind of canonically, we use z as our variable when describing a complex number. So just some a plus bi. We say that the trigonometric form for that complex number is r times the quantity cosine theta plus I sine theta, where r is that absolute value of the vector, or its modulus, or even you could say magnitude. And the tangent of that theta should satisfy b over a. So we've gone and we've built out these two ways of representing a complex number, right? We have that standard form, the a plus bi. We have this trigonometric form, r times cosine theta plus I sine theta. So what do you suppose we do now that we have two forms? We want to talk about going back and forth between them, yeah. Oh boy, that's weird. Okay. So it says to find the trigonometric form for the complex number, so where theta is between 0 and 2 pi of negative 2 plus 5i. So the first thing I'm going to do is calculate the absolute value or modulus of my complex number. which is just a squared plus b squared, all square rooted. Negative 2 squared plus 5 squared is 29, and 29 is prime, so I'm not going to worry about trying to simplify that radical. So that's the magnitude piece. The next thing is I need that direction. So if I think about that, negative 2, 5 is like up here somewhere. So that's my direction, right? I want my answer in radians. I can tell because it tells us I want the theta between 0 and 2 pi. Since there's pi's in there, I know I want a radian answer. So this is like my alpha. So in this case, theta is going to equal pi minus alpha. And alpha is just going to be the tan inverse of the absolute value of b over a. So I'll go to my calculator right quick. Make sure I'm in radian mode. We'll do pi minus tan inverse. And I'm going to do the absolute value just in my head there rather than in the calculator because, quite frankly, I don't need the calculator to drop some negative signs here. It's not worth the button pushing to get the absolute value symbol to come up. I get 195. So then I would write z is the square root of 29 times cosine of 195 plus I sine 195. And it's basically exactly the same as a vector problem we had already done way back in chapter, I don't know, like 8 or something, right? Well, that's pretty cool. I love it when like something new just turns out to be the same thing as something old just with a different wrapper on it. That's pretty nice. So what we're going to talk about next is multiplication and division. Oops. So let's say I have two complex numbers, a plus bi and c plus di. And I want to multiply those two together. Well, it's just going to be a plus bi times c plus di. What would I do to multiply those two things? No. Yeah, I would just FOIL, right? This is, yep, that's all we're doing. These aren't vectors, so it's not a dot product. They act like vectors, but that's not what this is right yet. We have to use a little bit of imagination before we see the vector connection here. So I have, if I FOIL that, I get AC plus ADI plus BCI plus BDI squared. What is I squared again? Yep, I squared is -1. So that's going to simplify down to AC minus BD plus the quantity AD plus BC times I. So that's what I would have to do if I want to multiply two complex numbers out that are in standard form. Basically, I'm stuck foiling, right? So if I had 10 complex numbers multiplied together, it's 9 sets of FOILs that I have to do, like FOIL and simplify, multiply the next one, FOIL and simplify, multiply the next one, FOIL and simplify, multiply the next one. I'm ready to poke my eyes out. It's true, like, tell me that we don't have to do this every time. Well, what else could we try? What if we put these into trigonometric form and see if we can find a way to make this any easier? Everybody with me so far on that idea? Right? So just set it up the same way. All right, so if I want to multiply these two things together, well, the R1 and the R2 can just multiply each other together. But the cosine theta 1 plus I sine theta 1 times cosine theta 2 plus I sine theta 2, still have to FOIL that out. Yuck. All right, well, let's get after it then, Mr. Kulik. This does not seem like it's making life any easier. Well, you know what? Sometimes you just got to give it a chance. And maybe something nice will happen. And at this point, you should start thinking to yourself, oh, Mr. Kulik, like, I don't believe that you would have us waste your time and our time if something good wasn't eventually going to happen here, but I don't see it, and I'm getting kind of dubious that something good's going to happen here. I would just say patience, grasshopper, patience. Okay, so I just foiled that thing out, and at this point you're like, this is way worse than before. I don't know get why we're doing this. This stinks. That was so much writing. All these stupid 1s and 2s. I am having a hard time keeping everything straight. Well, okay, granted. What I look at next, I see that I squared, so that's just going to become -1. So if I group this stuff together, oops. I have the stuff without the i's, so cosine 1, or cosine theta 1 times cosine theta 2 minus sine theta 1 times sine theta 2, plus I times cosine theta 1 sine theta 2, plus cosine theta 2 sine theta 1. Do you see it? Do you recognize that? Cosine 1, or cosine theta 1 times cosine theta 2 minus sine theta 1 times sine theta 2? It is a identity. Yeah, it's the angle sum identity for cosine. And how about this one? Cosine theta 1 sine theta 2 plus cosine theta 1, or theta 2 times sine theta 1. Guess what that is? It's another identity. It's the angle sum for sine. So what do we end up with? We have So hold on a second now. What do I have here? If I multiply two things in trigonometric form, what do I have to do? I just multiply the magnitudes and add the directions. Done. Do I have to FOIL? No. So if I need to multiply 10 complex numbers together, if they're in trigonometric form, I just multiply all 10 of the magnitudes together and add all 10 of the directions together, and I'm done. Ooh. That is a big upgrade over standard form, where I have to FOIL every single one of those little buggers out. What we've done is basically just turn this into a mental math problem. So let's look at a quick example here. Make sure we drive this point home. So Z1 times Z2. Z1 times Z2. Feels like I have some kind of weird accent. Okay, well, it's just going to be the magnitudes multiplied together and the directions added together. Done. That's my trigonometric form answer. Ooh. Real nice. How do I turn that into standard form now? Just use my calculator. So I'm going to do 28 cosine 185 and then 28 sine 185 and just tack an I onto that last number, and I'm done. To do that, though, what mode does my calculator need to be in? Degrees. How do I know that? Because that little degree sign next to the angle. Yeah, you got it. So 28 cosine 185. And then 28 sine 185. So I have negative 2789 minus 244i. There's my standard form version. That ain't too bad. Hey, what if we wanted to do division then? So we remember back to algebra 2, how did I divide two complex numbers in standard form? Do you remember how to do that? We did it last year. Well, we didn't. I mean, you did it. I've done it like 100 years, but, you know, not 100 years. I'm not 100 years old. Dog years. Yeah. But so are you. So, like, what's the big deal? We got to multiply the top and bottom by something. Do you remember what we multiply the top and bottom by? The conjugate of which one? The bottom. The bottom. So the conjugate is the same thing with just the opposite sign in the middle. So to do that, though, what are we going to have to do? Whole bunch of foilings. Yuckarooski. Well, I notice at least in the denominator, those cancel out. And then the I squareds both become negative ones. But that's like kind of a pain, right? Little bit of a nightmare. Yuck. What if we tried doing this in trigonometric form, though? How did it work for multiplication? Just multiplied the magnitudes and added the directions, right? What do you think division is going to look like then for trigonometric forms? Remember, for multiplication, we multiply the r's and add the directions. When we divide, what do you think we're going to do? Yep, and what are we going to do to the r's? No, we're dividing. But yeah, the same idea, which, ooh, Boise, that makes life like a lot easier. I don't know why you're trying to hone into my space there. All right. So Z1 divided by Z2. I'm just going to divide the r's. And then I have to subtract the thetas. To subtract pi over 3 and pi over 7, what do I need? Great. What would that common denominator be? So that would be 7 pi over 21 minus 3 pi over 21. So just 4 pi over 21. Done. Ooh, Mr. Kulak. That ain't too bad. Well, that's the trigonometric form. If I want the standard form, what am I going to do with that? Type it in my calculator. Keep in mind, though, that we're back into radians, so I have to change my mode again. Just flippy-floppy. Flippy-floppy, back and forth. Mode change, mode change. Got to pay attention. So, oops, that's for sine. I don't know why I did sine first. That's going to confuse me. Then I need to do the one for cosine. So I have 578 plus 394i. How you guys feeling so far? Right? So far, what have we done? We've talked about what a complex number is, how to translate it using magnitude and direction into a trigonometric form. We talked about adding and really subtracting complex numbers. We've done multiplication, division. Guess what 2 operations we're going to do next? Powers and roots. All right. So if I had like some complex number to the 10th, like 3 minus 4i to the 10th, and I wanted to do that out in standard form, what am I going to be stuck doing? A lot of foiling, right? Just 3 minus 4i times 3 minus 4i, get an answer, multiply it to 3 minus 4i again, get an answer, multiply it to 3 minus 4. Just like a bajillion multiplications, right? There's really no way of doing that any easier without the binomial, the binomial expansion formula, which is not really going to be much nicer to use. But what if we tried doing this in trigonometric form? So let's say we have some complex number in trigonometric form. Z squared is just z times z, right? Well, if I use my multiplication rule that we just developed, I'll just multiply the r's and add the thetas. And then what if I try z cubed then? Well, that's just going to be z squared times z, right? So if I do the same thing, I multiply the r's. R squared times r to the first is r cubed. And I'll add the thetas. 2 theta plus 1 theta is 3 theta. And at this point, I kind of see the pattern, right? 5z to the power n, what should I get? I get r to the n times cosine of n theta plus I sine n theta. This guy, this formula here that we just developed has a name. It's called de Moivre's theorem. Oh. So let's just do a quick example. So let's see, I have going to have 5 to the 5th cosine of 5 times 14 plus I sine 5 times 14. I don't know 5 to the 5th offhand. There you go. And 5 times 14 is 70, but I'll type in my calculator just to be sure. So there's my trigonometric answer. Boy, that was a heck of a lot faster than doing 5 foils, wasn't it? And if I want that in standard form, all I do is I go back to my calculator. I go back in the mode, because I got to switch back to degrees. Just back and forth, back and forth, back and forth. Flippy floppy, flippy floppy, flippy floppy. Super annoying. Mr. Kulik, why didn't you arrange your questions in a more sensible pattern so I didn't have to go flippy floppy, flippy floppy, flippy floppy past back and forth, back and forth, back and forth. I don't know. I'm a jerk, I guess. 1068.81 plus 2936.54 I. Well, that's really nice. That's quite easy, right? No big deal. Everybody still doing okay? What if we wanted to talk about roots then? So think back to your Algebra 2 class. What's the nth root of x the same as? What's that? X to the 1 over n. Excellent. So if I take that and like plug it into that de Moivre's theorem that we just developed, where like I'm just replace all the n's with 1 over n's, we'd have what? Z to the 1 over n equals, well, let's write it as the nth root of z, equals the nth root of r cosine of theta over n plus I sine theta over n. And that looks like it, right? Like, okay, that should be everything. What do you guys think? Should be dubious when I ask you questions like this. It seems like a loaded question, like I'm trying to get you to agree with me and I just go, no! Which is what I'm doing right now. So there's a little bit more to it than this, although this is close. What do we still have to worry about here? Well, if n is 0, that's not a root anyways, right? You can't take the 0th root of something. So n can't be 0, but that's the kind of loophole that we're looking for. But that doesn't apply in this case because you can't have a 0th root. So n being 0 just is, not possible for this kind of problem. Well, let me ask you this. Let's say I wanted to do cosine of 90 degrees and cosine of 450 degrees. What can I say about those two things? 90 and 450. They are coterminal, so what are their cosines going to be? The same. So, what if we have some coterminal stuff going on here? What's that mean for us? Is we're going to have more than one possible answer. How many answers am I going to get? I'm going to get n possible answers. Let's do a couple of numeric examples to drive this home. This is the most complicated thing we've done so far. So we'll do 2 of these just to make sure we kind of got it. Okay. Find the cube roots of 3 minus 2i, and then we're going to give our answer in standard form. It's the first thing that I would need to do here. What form is my complex number written in? Standard. What form do I want it in to do all the operations? Trigonometric. What's the first step going to be? Convert it to trigonometric form. Good. So r is just going to be 3 squared plus negative 2 squared. It's the square root of 13. And then to get theta, if I plot this 3 minus 2i, It's going to be down here somewhere. So that's my theta. What measure should I measure this angle in, radians or degrees? Does it matter?
No.
No, right? Nothing is indicated. Do whichever one you like. Most of us probably feel more comfortable in degrees. Let's do that. So there's my alpha there. So that'll be 360 minus alpha. So when I do that, I get and I gotta go back and check what mode I'm in. Does anybody remember? Looks like it must have been in degrees. Yep. Okay. So I get 326.31. So that's going to be the cube root of the square root of 13 times cosine of 326.31 plus 360 times 0 divided by 3 plus I sine 326.31 plus 360 times 0 divided by 3. That's one answer. My second answer is going to be the same thing, except we'll have 360 times 1. And then my third answer will be the same thing, except we'll have 360 times 2. Okay, so let's simplify this a little bit. What's the cube root of the square root of 13? Well, remember that a radical is the same thing as a fractional exponent, right? So that's really the 13 to the 1/2 to the 1/3. Now, how do I do an exponent of an exponent like that? You multiply the exponents. So 1/3 times 1/2 is 1/6. So that'll be the 6th root of 13. Actually, we wanted these in standard form, right? So I don't really care about that. But I'll write it as the 6th root of 13 just to make life a little bit easier. Okay, so there's two ways you could write the 6th root of 13. You could write it as 13 to the 1/6, 1/6, like that. Or you could press math and then choose option 5 and make the 6th root of 13 look like that. Either way is fine. They're doing the same thing, right? Everybody's cool with that? Okay. So let's get some numbers out of this. So I'll do times cosine of, and here I'm going to do the fraction command so that I can just go and do this over and over and over again. I'll take my 326 number plus 360 times 0, and then my divides by 3. Enter. So that's my first real component. And then I'll just update that to a to 360 times 1. That's my second x component. And then I'll update that to 2. And that's my third x component. Now to get my y components, to get my first one, I'm just going to go back here and change that to sine. That was weird. Oh my God. My pen was on my mouse pad and it just caused my calculator to have like a mini stroke there. Sorry. There's that first one. That's the imaginary component for the first value. And then I'll just update that to times 360 times 1. That's my second answer's imaginary component. And then update it to 360 times 2. That's my last answer's imaginary component. So 1452i, and then negative 1153i, and then negative 0.299i. I guess I'll take the plus signs out of there and just write them as subtractions. Right, so we have 3 answers for k equals 0, k equals 1, and k equals 2. Let's just pretend for a moment that we forgot that we're only supposed to get 3 answers out of this and say we tried getting a 4th answer. So let's say I did that cosine of that thing times 360 times 3. This is the real component I got out of there. Does that look familiar? Yeah, guess what's going to happen as I go through and keep doing this? I'm just going to get these same 3 answers over and over and over again. So the moral of the story is I used k equals 0, 1, and 2, right? But any 3 consecutive numbers are going to be fine. You could have done negative 1, negative 2, negative 3. You could have done 5, 6, and 7. You could have done 13, 14, and 15. You could have done 110,342, 110,343, and 110,344. It doesn't really matter which 3 you choose. Well, that's pretty nice, right? Like, so if I did 1, 2, and 3, I would have gotten the same answers. Yes, they would have come in a different order, but that's fine. We don't care about that. Everybody feel okay? Let's do one more example of this and call her a day. What do you say? Yep. All right. So let's say we asked you to find the 4th roots of 16. Well, until today, what have you said the answer to that is? 2, right? You got 1 of them. You got 2 of them. There's 2 more. All right, so the first thing we're going to do is we're going to recognize that 16 is a complex number, 16 plus 0i, and we're going to convert that into trigonometric form. Well, should be pretty easy to see that r is going to just be 16. The square root of 16 squared plus 0 squared is just going to be 16 again. If I plot that, 16 plus 0i is just there on the x-axis. So what angle is that? Theta equals 0. Good. So we have 16 cosine 0 plus I sine 0. Everybody's cool? So 4 through to 16. I'm going to write this in kind of a condensed form. It's going to be the 4 through to 16 times cosine 0 plus 360k over 4 plus I sine 0 plus 360k over 4. And then I'm just going to write down the 3 values of k that I'm going to plug in. I'm going to write, this is the way I'm going to format my answer. I'd encourage you guys to do the same thing. I wrote everything out in the previous one so like you could understand what I was plugging in. But like, that's what I would write down. Everything else I'm just going to do in my calculator. Everybody's happy there? All right. So 4 through to 16 is just 2. And I have cosine 0 plus 360 times 0 over 4. That's 2. And then we'll update that 0 to a 1. That's 0. Update that 0 to a 2. That's negative 2. And we'll update that 2 to a 3, and we got 0 again. So those are the real components for my first 4 answers. And we just need to do the imaginary part, so I'll just update that to be 2 times sine 0 plus 360 times 0 over 4. So I get 0. And then I'll update that 0 to a 1. Get a 2. And then my 1 to a 2. That's a 0. And then my 2 to a 3. That's a negative 2. So those are my 4 answers. I really have 2, 2i, negative 2, and negative 2i. There's my 4 answers. Everybody's cool with that? No big deal, right? Guess what we just did? Is it the entire chapter 11? Yeah, that was it. We did one, then we did all of chapter 11. So here's what we'll do. We're going to take tomorrow and Friday, just general work days. Okay, since there's a lot of homework problems in this chapter. Most of them are pretty fast. You've seen the longest problem right here. That's the most time-consuming thing we ask you to do is this, something like this right here. But there's a lot of them, and we just did the whole chapter in one day, so like you guys need some time to process and work on some stuff. So we'll take Wednesday and Friday as work days, and we'll do the test the full class day next week, so Tuesday next week, and then Wednesday I think is an X day.
I think Monday's next day.
Is that what it is?
That's what I mean.
Okay. Whatever it is, the full class day, we'll take the test, and then go into break.
So Monday would be like a routine.
Sure. Whatever the X day is, I was planning on just not really doing anything new.
Okay.
Because this is a wonderful spot to end at because it's the end of the chapter. If the full class day comes before the X day, we'll just kind of like twiddle our thumbs on the X day. If the X day is before the test, we'll just have more time to work on your stuff and do questions and all that kind of jazz. I did put in the chapter 11 test review here. We're going to make this optional since the problem set is awful big. The review packet is optional because the problem set is rather large. I think it's 120. But here, hold on. Look at some of the problems that are on there. Look at like 21 through 40. Convert the following complex numbers into standard form. All you're doing is typing this in your calculator and pressing enter. Right? There are problems that are just like that are like, okay, that's like a nothing burger problem. Or plot them in the complex plane. Like, come on now. You're just plotting a point. Like, that's a nothing burger problem. Go ahead.